Hello everyone, welcome to this demonstration where I'm going to show you one of OPAL-RT's new products that's going to allow you to more efficiently test and develop your battery management systems. My name is Reef Hamada. I'm a technical sales specialist here at OPAL-RT, and the product that I'm very excited to show you is called the Cell Monitoring Device Emulator, or CMDE for short. Cell monitoring devices are battery management ICs or integrated circuits that measure cell temperature and voltages. They're found in all BMS systems and are a very central point in terms of development and testing. So here we've leveraged OPAL-RT's long history in FPGA simulation to simulate these devices on the FPGA. And this allows users to connect various software systems such as simulation models and hardware platforms in your hardware-in-the-loop setup. My main points of focus in this demonstration are going to highlight some key features of the CMDE tool. Firstly, I'm going to show you how we can emulate chips cascaded together, reading cell voltages. Second, I'm going to show you how we interface with a real physical BMS or ECU master using the digital front end of our FPGA. And third, I'm going to show you some interesting fault cases that are easy to do on software and may be a little difficult to do if you had the real hardware. So over here by my side, I have a PXI setup over here and my battery BMS emulator. So there's three main parts to this demo. First of all is the NI PXI chassis that's running NI VeriStand. And it's also running a Simulink battery chemistry model that's generating voltages for certain cells. Second is an FPGA, which holds the cell monitoring device emulator. As you can see, we support a growing list of chips. So if you don't see your chips on this list, don't worry. Contact someone from OPAL-RT and we'll tell you if we already support it or if we'll develop it. The last part is the emulated master, which in this case is a microcontroller, an Arduino, that's running a program that's able to communicate with the simulated chips on the FPGA. The way I've connected them, you can see, is from my microcontroller, I've taken out the SPI ports to a breakout box and connected that to the front end of my FPGA. On the screen over here, I have NI VeriStand open. For those of you who don't know, NI VeriStand is National Instruments real-time management platform. It allows me to control various simulation models and real-time sequences and various pieces of hardware such as analog I/O, digital I/Os, an FPGA card, communication protocols such as CAN, LIN, and automotive Ethernet. So, what does our device look like over here? I've set up an emulated ring of 4 cell monitoring devices. The cell monitoring devices that I've chosen are LTC6811 chips. And you can see them over here on this GUI. We have 4. The tool or the product also includes 2 SPI ports, SPI port A and SPI port B. That allows your master to read and communicate via the first or the second or both for redundancy purposes. We also have pinouts that allow you to connect to external LTC6811 chips, allowing you to mix a real hardware test along with a simulated test, or another FPGA that has an extended ring. If your battery management system is speaking to that many rings that they don't fit on one FPGA, we can always cascade different FPGAs together. So if we go down and look at the device configuration for each one of these devices, you'll have a mode index that allows you to enable or disable the device. So I'm going to go ahead and enable this device. You'll see it turns on. You can control every single voltage for all 12 cells. The LTC6811 reads 12 cells, but if your other chips may read more or less cells. And the product does accommodate this change of cells as well. And I can control each of these as a user. And these are known, for anyone who's familiar with NI VeriStand, as channels. Channels can be controlled via the user, like I'm doing here, or via a real-time sequence, a CPU model, or an external model such as one that comes from MATLAB Simulink. We also emulate the GPIOs so that you can better design your test cases. You can also set your regulation voltages, the temperature of the PCB or the IC, and the sum of the total stack voltage. I'm going to go ahead and turn all 4 of these on. So now we have all of them on, and they're ready to communicate with a master BMS. Another feature that we've developed is an application that goes on the Arduino that allows you to test the FPGA emulated chips. Over here you'll see I have this application open where you can select which device type we'd like to talk to. So here we select the 6811. You'll see all the commands that are supported, and you can write these commands. So that's going to send an SPI signal to the FPGA over here and receive a response. So if I want to send an RDCVA command, which is reading the first 3 cells of all 4 devices, I click write command, and then I'll see the raw data arrive. We also have a CRC check function. If you would like something a little bit more complex, you can also design your own test script. So over here, I've designed one that carries out 3 main functions. First, I set up an ADVC command, and then I read all 12 cells on all 4 devices using the RDC commands. Second, I have an ADAX command to read the GPIOs. And third, an ADStat command so that I could read all the status registers included within the chip. And if I go ahead and execute the script, you'll see the data blinking, and the CRC checks are okay, indicating that we have good data transfer between the FPGA and the master. And then we also have some more user-friendly graphic interfaces here. You can see the cell voltages that represent these cell voltages. And as I change them and re-execute the script, you can see that this changes live. You can see the various GPIO functions and also the raw data of the status registers. So this should give you a comprehensive view of what we're able to simulate and what you're able to control within your simulations to expand your test cases. Another interesting feature of our tool is the ability to create faults. For example, I'm going to show you a downstream fault. A downstream fault is breaking the link between 2 devices in the downstream direction. So if I set my mode on device 2 to index 3, you see I've broken this wire over here. When my BMS master decides to communicate with my FPGA, it's only going to see the first 2 devices. So if we go ahead and try that out, you'll see you'll only receive information and data from only your first 2 devices. If your BMS supports the redundancy port and can be connected to SPI port B, you would find out that you can read 3 and 4 from the second SPI port. And you could read devices 1 and 2 from the first SPI port, and therefore you can conclude that there's a wire broken between devices 2 and 3. You can also create an upstream fault on both directions. And then various other faults, such as a redundancy fault, a self-test fault, or a CRC response fault. And you'll see here that there's an issue on the GUI. Now, these are very powerful tools, as a CRC fault, for example, allows you to simulate the wrong type of data being responded by a chip. This would be very difficult to do using a real hardware platform. Thus, this gives you the ability to better validate the control and redundancy features on your BMS master software. We have various other diagnostics here at the bottom of the page, such as the uptime, so how long we've been running, the loop duration. So as you see, we've optimized the code to execute in 5 microseconds, and this allows you to connect very high fidelity simulation models to the cell monitoring device emulator so that we can keep updating the cell voltages at a very quick rate. And you also have a debug register. This shows you the last message sent forth by the SPI master. So that also allows you to validate your SPI master's messages. So that covers this demonstration. However, I'd also like to show you how you can configure your own configuration using your own chipset and your own number of devices. So I'll show you on VeriStand. You'll be able to go to the configurations pane, to the custom devices section, and that's where you'll find our cell monitoring device emulation tool. So if we look into this tool, you'll see the version number, the PCL decimation. So the PCL is the primary control loop of your whole real-time simulation time step. And 10 indicates that we're running 10 times slower. So you're running the CMDE tool 10 times slower than the time step. And the FPGA device name so that you can indicate which FPGA device you would like to load your configuration onto. And now I'll show you the various configurations that we have. We have ones that support LTC 6811s, 6810s, and other devices, and even combinations of devices. The configuration description will show you what type of arrangement we have, the features, the commands supported, the operation modes that you could use, and the hardware pinouts so that you can connect a real device or an oscilloscope to it. When you're ready, you can click on the Apply Configuration and select the number of cells that you want to include within your chain. When you're ready, you can press OK. And you'll see that VeriStand will populate your devices over here. You'll see that each device is unique. For example, over here we have the ADBMS 6830 that supports 16 cells. It also supports a cell open wire function and the discharge function. The discharge is the rate of discharge of each cell. In our tool, we've added the rate of discharge function into the FPGA simulation so that if you select the rate of discharge of 30 minutes, it'll take a real 30 minutes for the cell to discharge. We also include a serial ID, for example, that allows you to add an identity number to each device in your chain. And now if we compare it with the second chip, it supports a different number of cells and different functions such as AVCC and the reference voltages. When you're done configuring your own setup, you can save this system definition file, as it's called. Over here, I'm going to continue with my own. And you'll see it being saved over here. Now, this allows you to do some very powerful testing. For example, you can duplicate the system definition file over here, and you can reconfigure a different setup with the cell monitoring device emulator. This may represent in your own testing a different battery pack or a different battery module with a different number of cells in series or in parallel, a different chipset. And then using your test sequence, you can select which type of system definition file you'd like to execute and then run your tests. And this is very powerful when you have various setups in your laboratory that you're trying to test. And instead of recreating a different project, you can use one project and one tool to cover all these test cases. I hope you found this demonstration very insightful and very useful for your own use cases. If you have any questions or you would like to find out more, please contact us at opalrt.com/contact us.